Okay, so let's go ahead and take a look at the next objective. So your next objective deals with finding the volume. And what you're going to do is you're going to take what we did with area, and what we're going to do is we're going to rotate that area about an axis or a vertical line or a horizontal line, and we're going to create a three-dimensional shape. Or what we're going to do, or it could be an and, we are going to superimpose a different shape on top of that area region that we did in a previous lesson. And we're going to find the volume of that new shape where we've superimposed all of these like squares or semicircles. And so and then we're going to create a three-dimensional shape in that way and then find that volume. So there's two ways of finding volume. One is if the equations are in terms of x, and the other one is whether they're in terms of y. And then whenever you do volume, even if I say find the volume of a solid, I could say something is solid even if it has a hole in it. So even if it is a washer, okay? And so whenever you do a volume problem, you're going to want to ask yourself first, is this a solid or is this a washer? If it is a solid, there is no gaps between the shaded region and the axis of rotation, meaning that one of the equations of the volume that the solid that is formed is actually also the axis of rotation. Meaning like you have an equation and it's bounded by the x-axis and it's rotated about the x-axis. So basically the axis of rotation has to also be one of the equations that makes up your volume. Otherwise it's a washer. So even if it has a small teeny tiny hole in it, it is actually still a washer, okay? So that situation is when your two equations that form the solid are not the axis of rotation, okay? So let's take a look at an example or two. And we're going to take basically the equation here. So this equation is negative x squared plus x, and I'm going to rotate it about the x-axis. And so what's happening is that it is coming out of the screen and going back through the screen. And when it does that, it's forming this like shape down here also, okay? And so this is a three-dimensional figure. It looks like, kind of looks like a football in a way. And so this is completely solid because it's bounded by the x-axis and it's rotated about the x-axis. So this is called a solid. Because this is coming out of the screen and going back through, the cross sections, if I were to draw a line and chop my little three-dimensional figure, my football, and take a look at it, at this cross section right here, then that figure that I'm showing you or you're looking at is actually a circle. So the cross section, when I slice it and I turn it towards me, it looks like a circle, okay? Because of that, what we're going to do is we're going to define volume to be the area of the cross section infinitely many times between the two intersection points. So volume is always defined as the antiderivative of area, okay? So if my cross section is a circle and my volume is equal to the antiderivative of area of a cross section, if the cross section is a circle, then I'm looking at volume being equal to some sort of pi r squared and taking the antiderivative of it. So a couple things that you have to find first. First thing you have to find is you have to find these intersection points, which it looks like 0 and 1 based upon the graph, but don't trust the graph. Actually do this algebraically or with your calculator. Take your negative x squared plus x and set it equal to 0. So then you You factor out a negative x, you get x minus 1 equal to 0, so x is actually 0 and 1. When I give you the graph or the figure, make sure that you double check the intersection points, because when the graph gets put on the paper gets photocopied. Sometimes the marking is just slightly off, and so you won't know if it happens to be actually 1 or a decimal point very, very close to 1. So always do it algebraically or by setting the equations into your graphing calculator and finding the intersection points. Okay? So in order for me to set up my antiderivative, I need to know what my radius is. So this entire line here is actually the diameter. So what I want is from the equation to the x-axis to give me my radius. Okay, if you struggle with what the actual radius is, pick an actual value for x and then calculate the distance between the 2 points. Okay, so if I were to pick 0.5, for example, in order to find this distance, I would have taken my negative x squared plus x, and I would have plugged in a half in for all of my x's. Okay, and I'm plugging it into the equation, and then I'm subtracting off my y equals 0, which you don't necessarily have to write, but in the end, the equation is actually your length of your radius. So no matter where I draw my radius, because I drew it at a specific point, I need to write my antiderivative as area of a cross section as any point that I choose. So something very, very close to the intersection of the x-axis, or something very, very far away. And so I have to generalize what my radius is, and I'm going to generalize it with the antiderivative of the equations. Okay, and in this case, just one equation. So when I look at volume is the antiderivative of area of a cross section, which area of a cross section is going to be pi r squared. In this case, I'm going from 0 to 1 because those are my two values here. And my radius is my negative x squared plus x. And then I'm technically subtracting off 0 to get my radius, the distance between 2 points, and I'm squaring it. Because it's pi r squared, I can move the pi on the outside if I want and multiply by pi in the end. Do not forget to multiply by pi, okay? So then my volume is equal to pi, antiderivative from 0 to 1, of negative x squared plus x, the quantity squared, dx. Okay, so now let's go ahead and take a look at the graphing calculator, but we did practice the graphing calculator in the last unit. Let me just show you Desmos real quick. Desmos is a free online graphing calculator. So if I have f of x, oops, and then is equal to negative x squared, and the negative in Desmos is just the same thing as the subtraction, and then plus x. Okay, so that's actually what my graph looks like. We can zoom in and you can see what that kind of looks like. Now, I'm going to go ahead and I'm going to take my antiderivative, which is here. So I'm going from 0 to 1, and then I've defined it to be f of x, so I'm going to go parentheses, f of x, close parentheses, and I'm going to square that. Oops. dx. Okay, now I'm going to take this result, which is 0.03, and I'm going to multiply this by pi. So I'm going to put the pi in the front. So I have pi times that integral, and I get 0.105. Remember, 3 decimal places, so 0.105. So that is my volume. So volume is approximately equal to 0.105. Okay? So now, let's take a look at, and you're always going to ask yourself, is this a solid or is this a washer? So remember, it is a solid if one of the equations that you have is also the axis of rotation. Now when I look, I have an f of x and I have a g of x, and then I'm rotating about the x-axis. The x-axis is not one of the equations, either f of x or g of x, so this is a washer. How this changes is that what I really want to do is I'm going to take the volume as if this was completely enclosed in, just like we do with area. Okay, and then I'm going to subtract off the part that I don't want, which is this empty space here. Okay, so I'm going to go ahead and I'm going to set up my equations. First thing I need to do is I need to find my intersection points. So I do that by setting the equations equal to each other. So I have the square root, I guess I can do it over here, the square root of 25 minus x squared is equal to 3. And I could also do this by plugging it into the graphing calculator, plugging in my f of x into y1 and my g of x into y2, and going and graphing and going second trace and intersect. Okay, so 25 minus x squared is equal to 9. So x squared is equal to 16, so x is equal to plus or minus 4. So my intersection points are at -4 and 4. And these are x values because I want x values for my intersection points if I have x variables on the inside. You're going to use y variables and y intersection points if those two match. Okay? So now I need to figure out which equation is the outermost equation, and then that is going to be a pi r squared minus what is the innermost equation. And the reason why it's pi r squared is because as this is coming out of the screen and going back through the screen, the cross section is a circle. You will always get the cross section to be a circle if you are rotating it about a line. Okay, and then let me also be clear. If I'm rotating about a horizontal line, then I have x variables in the integrand and x values for the intersection points. Okay, so if you rotate around a vertical line, and the x-axis is a horizontal line, if you rotate around a vertical line, then it's going to be different. Y variables in the integrand and y values for your intersection points. And they always match up that way. Okay? So when I write my integral, the outermost region is my f of x. So my volume is equal to pi. And then I have, we can have pi way on the outside, -4 to 4 of my f of x equation squared, so 25 minus x squared dx, and then minus -4 to 4 of my inner radius, which is 3n squared. So they are squared, they call it squared separately when it's a washer. okay? So I would use my graphing calculator. Don't forget to multiply by pi, and you get volume is approximately equal to 268.083. Easiest thing to do is to plug in your f of x to be y1 and your g of x to be your y2. Okay? So now we've rotated around horizontal lines, and horizontal lines tell you x variables in the integrand and x values for your intersection points. Now what happens when I rotate around a vertical line? Remember that the y-axis is a vertical line. So we're going to take this solid, and I'm bounding it between x equals 0 and 3. I'm rotating it about the y-axis. Because I'm cutting it off at x equals 0, and that is the same as the axis of rotation, then this figure is a solid, okay? We will then figure out what the intersection points are. We would normally look at 0 and 3, but because I'm rotating around a vertical line, then I need to have y variables in the integrand, and y values for the intersection points. Okay, so the y values are actually 9 and 0. The way I find them is this equation is y equals x squared. So when x is equal to 0, y is equal to 0. When x is equal to 3, y is equal to 9. And now, this is still, because I'm rotating it about an axis, this is still volume is equal to pi r squared. But now my volume is from 0 to 9, and then I have my pi on the outside. Instead of y equals x squared, I have x is equal to root y. So I have to change my equation to be in terms of x equals, and I'm going to plug in my root y in for my radius squared and then dy. Okay. Again, because this is y, I can trick my calculator into thinking that it's x by doing the antiderivative as if it was x, okay, which was in a previous unit or a previous section that we just did. When you find your antiderivative, you should get 127.235. Okay. Again, when these are polynomials, I can ask this on a non-calculator free response test or a non-calculator multiple choice test. Okay. So I've been having the axis of rotation being either the x-axis or the y-axis. So now what happens when the axis of rotation is something different? So let's look at example 4. Example 4 is your axis of rotation is now the line y equals 1. So now the question becomes, is this a solid or a washer first? Step 1, solid or washer. I am rotating about the line y equals 1, and y equals 1 is one of the equations. So this is a solid. I then find my intersection points by setting my equations equal to 0, or plugging one of them into y1 and plugging one of them into y2, hitting graph and finding second trace to calculate the intersection points. But here I did set them equal to each other, and I got x equals -1 and 1. Because I'm rotating around a horizontal line, I need x variables and x values. So I don't have to find the corresponding values, y values for -1 and 1. Okay? Now, how do you calculate the distance between these 2 points? And this is where it's going to get a little tricky. So you have to go back and think to like previous classes. how did I calculate the distance between 2 points? What did I do? Well, typically what you do, change colors here, is you take a certain value for x, so like x is equal to not 1, 0.5. And you take this 0.5, and to calculate the distance between my f of x and 0.5, to calculate the distance between these 2 points here, between my f of x and my g of x at 0.5, I take my 0.5 and I plug it into f of x. So I would get 2 minus 0.5 squared. And then I would subtract off 3, because the distance between this coordinate point and the x-axis is 3. So because of this, I would take my f of x equation and I would subtract off g of x. This would give me the radius at any value of x. So even if it was closer to the y-axis, I would take my value at f of x and I would subtract off 3, which is my g of x equation. So now for the integral, I have pi. I'm going from -1 to 1, and I'm squaring my r. My r is f of x, which is 2 minus x squared, and then minus 1, and then I'm squaring it, dx. And when I use my calculator to evaluate, which I would have done that by plugging this into y1, oh, I'm sorry, this was not 3. I apologize. I'm subtracting off this y value of 1. So it's f of x minus the g of x, which the g of x is 1. I apologize, I was confusing examples together. So my volume would be 3.351. Okay, so since I confused my values, let me go back for a second. So if I wanted to calculate the distance between these 2 points, I plug in my 0.5 into my equation for f of x. Then I'd have to subtract off this bottom part, which this bottom part, the distance between g of x and the x-axis is 1. So I subtract off 1. Because of that, it is f of x minus g of x anywhere I happen to pick my value of x. So then that's why I have my f of x that came first and my g of x that came second. Okay? This is a little bit of a lengthy lesson because there's a lot of stuff related to volume. Okay? But I will answer any questions that you guys have about this. Because now we're going to switch gears a little bit. There's a different type of volume that you can get. And then we are going to talk a little bit about something that that has to do a little bit with area, only because I want to show you guys how you can see free response type questions. Okay. So let's take a look. Let R be the region bounded by the y-axis and the graphs of y equals x cubed divided by 1 plus x squared. And the equation y equals 4 minus 2x. The region of R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Okay, find the volume. So what that's saying is cross-section perpendicular to the x-axis means that this orange spot here is a cross-section perpendicular to the x-axis because the cross-section is going vertical and then the x-axis is horizontal. Cross-section perpendicular to the y-axis would have changed it to go right to left or left to right. That would be cross-section perpendicular to the y-axis. What it means by cross-section perpendicular to the x-axis is a square. That means that when you find the volume, remember volume is the antiderivative of area of a cross-section. Okay, and so the area of the cross-section is a square, which means that my volume is going to be something, some side squared. Okay, there's no pi in the area formula for a square, so you don't have to worry about pi. The only reason why there was pi in the previous example is because your cross-section was circular, and the area formula for a circle is pi r squared. So we're going to do the exact same thing we've done before. Again, do not trust your intersection points. Now let's be clear. Perpendicular to the x-axis will mean x variables and x values for your intersection points. So I'm going to set my equations equal to 0, or you can plug one of them into y1 and one of them into y2. Okay. When you set them equal to each other, or you plug it into the graphing calculator, which you're probably going to have to plug it into the graphing calculator because you get a cubic that doesn't factor by grouping. So your only option is rational root theorem, or I would just use the calculator for now. Okay, cross the bridge when it comes up if you don't have a calculator and it's a cubic and you have to use the rational root theorem. So let's look. When I use my graphing calculator, I will tell you that I get 1.4876664. Use as many decimal places as you possibly can for a intersection point. Okay? We are looking for the area formula for a square, so you need to figure out what the length of the square is. So let's be clear. My line, which is my y2, so this is 4 minus 2x above, and then my cubic over my 1 plus x squared is actually in the bottom. So the distance between this top equation and this bottom equation is subtracting both of those equations from each other. So that means that my volume is equal to the antiderivative from 0 to 1.487664. Again, use as many decimal places. Do not round until you get to your final answer. Okay? Do not round in between. So I have my 4 minus 2x first, and then my x cubed divided by 1 plus x squared second. And because this is the area formula for a square, this is the side length, and so we are going to square it and then tack on the dx. When you use your graphing calculator, you will get 8.997. Okay? All right, last one, I promise. And then we will have a day or so to kind of work on these problems. Okay? So this last example here, the region R is bounded by the graph of y equals x squared and the line y equals 4, as shown in the figure below. There exists a number k where k is bigger than 4, so above the axis of rotation, that when r is revolved about the line y equals k, the resulting solid has a volume of 256 pi over 5. Let me be clear. There is a gap between k and the line y equals 4. So even though I said that the resulting solid has a volume equal to that, this is actually a washer. I can classify a washer as a solid. So we use the idea of a solid in directions very, very loosely. Okay? So if this volume is equal to that, we're going to rotate this equation around, which means that I need to calculate the distance between my axis of rotation and the furthest part of my graph. Okay, so what's the distance between these 2 points? Well, this value here is something on y equals x squared. but I'm taking my k and I have to subtract off this little y value here. So my outermost radius here is k minus x squared. My innermost radius is the distance between these 2 points. And the distance between these 2 points, this value gives you k, but that goes all the way down to the x-axis. So this value here is k minus 4, because I would subtract off this whole distance of 4. Okay, so now I'm going to set this up. It says write but do not evaluate. So I have 256 pi divided by 5 is equal to the antiderivative. Now, I'm looking for the antiderivative. I need to figure out what these two values are. So what happens when x squared is equal to 4? X is equal to plus or minus 2. So negative 2 to 2. And then I have my pi. Let's put pi on the outside. My outermost radius is k minus x squared, and then minus k minus 4 squared, and dx. So I have this weird looking volume, and that's actually my answer. So I'm taking, again, when you do washer, you're taking the radius of the outermost function, subtracted off the radius of the innermost function. Okay? And that is it for this lesson.